Is it? Can you tell if it's recording? I can't tell if I'm recording.
Yeah, it's recording.
Yeah.
It is. Okay. I think you see a little light or something, right? Oh, I see it too. There we go. Go. Any questions before we get started? No?
Joke question or math question?
Whatever you got.
Let's see, because half of me is almost tempted to do the Monty Python question, or
Oh, which Monty Python question?
well, is there multiple?
Oh, I don't know. Isn't there? I just watched Holy Grail a few days ago.
Yeah, and then all that I'm thinking of is the Unladen Swallow.
Oh, that one. Yeah, right. No, I mean, isn't there lots of? Oh, all right, never mind.
And I feel like that one's the iconic one, though.
True. Yes, at least for a math class. Let's see. Okay, so back to the basics. We got rings. You should be able to show whether a certain set with some operations is a ring or not. So be able to determine whether a given set together with operations is a ring. Now, you typically don't want to have to do this from scratch. What you really hope is that your ring or your set is a subset of a known ring, and so then you can just apply the sub-ring test. So hopefully you can use the sub-ring test. And so to apply the sub-ring test, you need to have sort of a list of known rings, right? And so the standard rings right, Z. I'm not going to write them all down, but Z, Zn, Q, R, R bracket X, Z bracket square root of N. There's matrices. And so on. So if you happen to have a set and recognize, oh, it's actually, lives inside one of these known rings, then you can just apply the sub-ring test. What else we got here? Ring homomorphisms. We introduced them in this chapter, although we didn't do a whole lot with them until later on. Homomorphisms. Unit. Field. Next chapter is integral domains. And though, there certainly are rings out there that are not integral domains, this is sort of the minimum, right? Having zero divisors just kind of makes things a pain. So it's nice if you're at least working in an integral domain. So notice a lot of the theorems that we had in this class had the assumption that we were working in an integral domain. So zero divisor. Cancellation holds here. Oh. Right. In fact, cancellation is equivalent to being an integral domain, right? Cancellation if and only if no zero divisors. Every field is an integral domain. It's not true in reverse, but of course, and you prove this on the midterm, that finite integral domains are fields. Characteristic. (21) is field of quotients, and as before, I mean, you just need to know that there is such a thing and how what it is, right? I mean, it's a set of equivalence classes, which you can then think of as the set of fractions under the usual equivalence relation, right? Two fractions are the same if they're equal, or if you get the same result when you do cross multiplication. So polynomial rings, a couple of facts here. If D is an integral domain, that tells us that D bracket X is an integral domain. And then there, the key tool, or one of the key tools of studying polynomial rings, is evaluation. All right, so we call that phi sub alpha, and it goes from F bracket X into E, where E is the field that holds alpha. All right, so it turns out it's a homomorphism, and it's a useful homomorphism. Next chapter, factorization. In F bracket X. So this is a pretty long chapter where we did quite a bit of study of polynomials. We got a division algorithm for polynomials. We talked about irreducibility of polynomials. And okay, we defined irreducibility in D bracket X, but then most of the time we work in F bracket X, so there's a sort of easier way to think of it, of what it means to be irreducible in F bracket X. Then there's the tests. And the main ones that you want to, or I'll write them down here. So I mean, of course, there's the degree 2 or 3. What else? I'll say it like this. So if you have an integer polynomial, then if you can factor it over Q, so if it's reducible over Q, that tells you that it's reducible over Z. So let's put some, so there's the next one. I sometimes call this the integer root test. Rather than the rational root test. So that's the one that says, you know, if you have f of x equal to a0 plus a1x plus dot 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 plus an minus 1 x to the n minus 1 plus x to the n. So we have a monic polynomial where the coefficients are in Z. And we don't want A0 to be equal to 0. So A0 not equal to 0. So if f of x has a rational root, then it actually has an integer root. So then there exists b in z such that f of b equals 0, and b divides a0. So essentially what this says is, if you're going to have a rational root, then it needs to be an integer that divides the constant coefficient, right? There's a mod p test. And then Eisenstein. Any questions so far? So next chapter, 26, that's homomorphisms and quotients. So you should be able to, you should know and be able to prove the properties of ring homomorphisms. Ideals. And the ideal test. We talked about the ideal generated by some set of elements, right? I'll just write it as angle bracket. So ideal generated by and there doesn't have to just be a single element in there, right? That can be some collection of elements in your ring. Kernels are ideals. R mod I. First isomorphism theorem. I think I had you prove the first isomorphism theorem for groups. There's not a whole lot more to prove for rings, right? There's a couple extra things we have to look at, but 27 now, prime and maximal. Ideals.
I have a quick question.
Yeah.
What does it say under ideal test?
So you mean this stuff here?
I can't read like the words after that.
Oh, ideal generated by.
Okay, thank you.
Let's see. Oh, in a commutative ring with one. An ideal, so an ideal I is equal to R if and only if I contains a unit. We define maximal ideal. And often the property right above that shows up quite a bit when you're trying to prove that something is a maximal ideal directly. Um, I is maximal if and only if the quotient is a field. We also define prime ideal.
I have a question.
Yep.
Because you often have definitions in the beginning, and we have the prime ideal versus like a prime like element or something. Would you have would we need to list both of them if you ask for prime, or would you distinguish between the two?
I'd be clear. I mean,
Okay.
you know how I usually do my definitions, right? I kind of get it going anyway. So I would say such and such is a prime ideal, or such and such is a prime element. Yeah, I'll be clear on that. Yeah.
Okay, perfect.
Oh yeah, and so then an ideal is prime if and only if R mod I is an integral domain. From this, then that tells us that maximal implies prime. So principal ideal. Principal. Principal ideal domain, so PID. And then we're able to show that a field, if you have a field, then F bracket X is a PID. So F bracket X is a PID. And then this, so in F bracket X, the ideal generated by F of X is maximal if and only if F of X is irreducible over F. And there was an application of this. This allowed us to construct fields of given orders. Right? So application of this. And also in this chapter, we showed that factorization is unique in F bracket X. So I'll say unique factorization in F bracket X. This is long before we defined UFD. Well, maybe not long before, but it was before we actually defined the more general concept of UFD. We showed essentially that F bracket X is a UFD. Chapter 45 is then about unique factorization domains. So we defined what it means in a ring for one element to divide another. We defined what it means to be an associate. We define irreducibles. So let's say and prime. Here as, yeah, so we define the more general concept of irreducible and prime elements in an integral domain. And then we notice things, the naming of things is a little bit backwards to how we think about it, right? And it turns out that prime implies irreducible, but not necessarily vice versa. So then we define UFD. There was the ascending chain condition. And we had to show that principal ideal domains have the ascending chain condition. And that allowed us to then show that principal ideal domains are integral domains. Also, in a principal ideal domain, the ideal generated by P is maximal if and only if P is irreducible, right? Which mimics the property that we have, or this generalizes the property that we know about F bracket X. So then in a PID, prime, prime is equivalent to being irreducible in a PID. And so, in fact, that gives you a way to show in certain cases that you're not working in a UFD. If you can find an element that is irreducible but not prime, right? Then you know that you are not in a not in a PID. Fundamental theorem of arithmetic. Next chapter, Euclidean domains. And I mean, so what's the point? I mean, what is it? What is a Euclidean domain? It's essentially a place where you have a division algorithm. A Euclidean norm has an additional property, right? It has that submultiplicative property. So, but a Euclidean domain has a division algorithm, or is a ring, an integral domain that has a division algorithm. And then our prime examples, Z, F bracket X, and Z bracket I. And then it turns out that Euclidean domain implies PID, which of course then implies UFD. So if you can show that you're in a Euclidean domain, then you know that you've got unique factorization. And then the last chapter, multiplicative norms. And the key property comes in the situation. So, right, we know that the norm, if you have a multiplicative norm, the norm of a unit is going to be plus or minus 1. If those are the only place, or if those are the only elements that have a norm of plus or minus 1, then you have this nice property that allows you to detect irreducibles, right? So if norm of u equals plus or minus 1 if and only if u is a unit. Then we have this property right here. If the absolute value of the norm of A is prime, then A is irreducible. And we found that this multiplicative norm idea is useful in working in Z bracket n, or Z bracket root n. Right, the multiplicative norm is a squared minus nb squared. And what do we know? As long as n is not equal to 1 and is square free, then it has this property up above. Right, and so that allows you to detect irreducibles. So I guess that's about it. So what do you got for questions for me?
The theorems.
Hmm?
The potential theorems that we'll be seeing.
Oh, well, okay, I didn't write down a list of them. I don't, it's not quite as cut and dry, I guess. So let me just kind of go through here. You want me to say, I guarantee you that one of these 5 is going to be on there. Is that right?
I
don't even
do,
know if I-
yes.
Yeah, I don't even know if I have that list for this time.
Do you have a general idea of how many problems will be on it?
Yeah, somewhere in the neighborhood of 10, I think.
Just memorize all the theorems.
Yeah, I mean, you could kind of. I'm going to
course.
go through here. I'll look. I mean, I'm not in a hurry, unless you're. I mean, are you in a hurry?
Not at all.
No. Okay. Let me see what I got here.
Is there going to be a true false section again?
Yeah.
Oh, probably. Do you want it? Do you want that or no?
No,
No.
definitely not.
Please, no.
Why?
That
Really?
was the hardest
No,
part.
no. Exactly.
Math true false is just really hard.
I don't write that hard of ones though, do I?
Comparative to the rest of the test, it was harder last time.
No kidding. I didn't realize that. I mean, it's here's where, I mean, here's the kind of things that true false allows you to, for example, all these quick little facts, like a finite integral domain is a field, right? Now, obviously I had you prove that last time, but now I could ask that in a sort of true or false form that doesn't require you to prove it. It requires you to know the fact, right? So there could still be one, even if you don't like it.
Okay, but
I
if I
don't mind
recall,
it,
that is
but it's
not
scary.
what the true or false was last time.
What was it?
I gotta find my exam now.
All right.
I just find it scary because there's no partial credit.
There's what? Oh, no partial credit. But I mean,
Yeah.
it's only like, what was it? 5 points or something?
I
10
think it's
points?
like 10.
10?
The self-doubt that I have is remarkable.
I see. Well, um, I don't know. You tell me what kind of problems or I'm gonna keep looking here.
Wait, are we writing the exam for you?
Well, I mean, it sounds like it. So,
Sweet.
okay, guarantee you're gonna have to prove a property of ring homomorphism. That's gonna be on there. And that could be, you know, how, so there's like the ones that before we introduced ideals, and then there was a couple of new ones that came after we introduced ideals. Kind of like a part 2 of properties of ring homomorphisms. Where the exam leave off? Where the midterm stop? Is that? Oh,
Right
it's like
before
Or
ideals.
cosets. Yeah,
right before cosets?
yeah.
Oh, it stopped at lecture 14.
Okay, so I didn't cover any quotient stuff on the midterm. Okay, that helps me. Okay, so you should know that. Okay, so here we go. Here's some guaranteed. So I already said properties of ring homomorphisms. The set of cosets R mod I is a ring if and only if I is an ideal. I guess I shouldn't use I, and it should be like R mod A. So R mod A is a ring under the natural operations if and only if A is an ideal. Theorem 27.3, that's sort of the classic maximal, I is a maximal if and only if R mod I is a field. F bracket X is a PID. There's not a lot of good theorems with names, you know?
The Euclidean algorithm.
What about Fermat's last theorem?
Yeah. No, not that one. 45.4. So yeah, maximal if and only if P is irreducible. Ideal generated by P, maximal if and only if P is irreducible.
Wait, could you say the number of that again?
45.3, I think. Right? I mean 45.4.
Okay, thanks.
Yeah, that's good. All right, so you're definitely going to get at least one of those. I can't remember if there's a multiple choice that goes along with this test. But okay, so River, did you find them?
I didn't. I don't. Maybe I'm like losing my mind or something. But I could have sworn we had a true false, right, on the last
Yeah,
exam.
but I thought
We
it was
did.
part of the Canvas.
It was the very last problem.
That's what I thought. I couldn't find it in my papers.
481 final, not our midterm that we had true false on.
Oh, okay.
Oh, well, that's why I didn't find it.
Yeah.
Okay, so I didn't.
Yeah,
put
those
one on the
problems were
midterm.
hard.
The ones on the final.
Those
I-
ones.
They were hard because I was like, oh yeah, it's true or false, and then every one of them like would have taken me 30 minutes.
Well, I don't know. All right, I'll think about it. I don't know. I mean,
Just give us an easy one.
yeah, I mean, I feel like the true or false, I guess they do make you say, oh, wait, am I missing some counterexample or something simple? Yeah, I can.
I mean, I think if they're part of definitions, that's one thing, but like, so I feel like some of the ones that were thrown in on the 481 final like took a decent amount of like rigorous proof, even though that work obviously doesn't show up in your answer. So it sort of compounds the time you're working on it. Like it's a deceptively long question. You know what I'm saying?
Yeah, I guess. I mean, I'm not worried about how long it takes you. Am I? Or am I?
Have mercy.
Mercy for the poor, please.
All right, I'm looking back and let me see what kind of, I'm gonna find it here.
Do you think the test is going to be more geared towards proofs or more geared towards computations? Because I feel like last quarter was about half and half.
I think it's half and half also.
Okay.
Because there's a lot of computations that you can do now, right? Checking
Mhm.
whether this thing is an irreducible prime, those types of things, ideals. Yeah, there'll be plenty of computations. And then there'll be
Oh.
some proofs also. So it's a mix.
I prefer less computations. I always make a mistake there.
Really? Well,
Last quarter, that was where I made all my mistakes.
it's a mix. I'm just looking at the one I gave last time.
Will it be like more focused on the new stuff past like the first midterm, or it'll be even-ish spread?
Sorry, try that again. You know, I had this sudden fear that I was actually showing you my old midterms, but I'm only sharing my iPad, not the entire desktop, right?
Yeah.
No.
Definitely.
No.
Yeah.
Share the desktop.
Well, I'm sorry, I missed the question now. Sorry, Brooke, go ahead.
Will it be like equal between like the different parts of the class, or it'll be more weighted towards the stuff after the first midterm?
I think more weighted towards the second half.
Okay.
In fact, probably close to entirely, completely weighted towards the second half. There might be a little bit of, sub-ring test or something like that, but for the most part, it's going to be quotients and forward.
Okay. sounds good.
With the exception, so here's the thing, is we have this theorem that says maximal ideal if and only if the quotient is a field. That can be combined with Eisenstein type questions now, right, to determine whether a certain quotient, a mod by an ideal generated by a polynomial, right, a quotient, say f bracket x mod ideal generated by a polynomial is a field or not, because now you can use the test to detect irreducibility to determine whether you have a field or not. That makes sense? I said too many words there.
No, that
Can you
makes sense.
repeat that real quick?
What's that? Repeat? Yeah, okay, here, in fact, I'm gonna write it down. Well, let's make sure I only share my iPad.
Thank you for sharing the desktop. Nah.
Mhm. Okay, now, so what I was saying is, we know we have this theorem that the ideal generated by little p is maximal if and only if p is irreducible, right? And so now, and this holds in arbitrary integral domain. Now, previously, we didn't talk about quotients on the last midterm, right? But what we could do now is I could say, okay, now let's, tell me whether, I can ask you the question, is this a field or not. Right? And the question hinges on whether that element right there is an irreducible. Kelsey, you with me?
Yes.
Okay. And so in particular, if we're working in F bracket X, I can ask you, is this particular quotient a field or not? And to answer the question, you want to decide whether that polynomial is irreducible or not. To decide whether it's irreducible, you're going to use perhaps Eisenstein or something like that.
All right, thank you.
Yep. And the division algorithm, what did I say? Do you have to prove the division algorithm?
No, you didn't say that one.
Yeah, I didn't think so. You'll definitely need to use the division algorithm. Right, we've used the division algorithm a lot and one of the main places that we use it is in getting a handle on a quotient ring, right? We start off by saying, okay, the quotient ring looks like this, but by using the division algorithm, we can say, oh, these cosets are equal to these cosets, so some of these are redundant. So it allows you to sort of eliminate redundant coset representatives. What else?
Quick question. Will you be able to post the solutions to the homework that was due yesterday?
Oh, yeah. Let me see.
Cool.
I
Thanks.
can do. I might be able to do it right now.
Okay.
While I'm thinking about it. I don't know how many people are in the class. Let's see. I need to know if everybody's turned it. I don't want to post it until people have actually got their homework in. When was it? It was due yesterday though, right?
Yep.
Yeah.
Yeah, I guess I could post it. Well,
If you look at Speed Grader, people who haven't turned it in have a little orange dot, and you can just like pull down their names and look real fast to see if anyone hasn't turned it in.
yeah, that's what I'm looking at. Well, I'm looking at the grade book and it tells me who has and has not. I'm just trying to decide whether I care whether the one person has access to that yet. I'm going to wait a little bit. Well, it's already late. Why do I care? Okay, I'll post it. And then someone just sent me a chat. Just a sec. Oh, you know what? Let me answer the chat question and then I'll think about that posting in a minute. So the question was something about, can you explain how the division algorithm helps us understand cosets? And I mean, maybe it's best done with an example. Yeah, in fact, this is a good example. So let's look at, yeah, in fact, let's do this one that we did this one in class. No, in fact, I'll do a different one. How about this? Okay, so here's a quotient. And so officially, this quotient is equal to the set of all cosets of the form f of x plus the ideal generated by x cubed plus x squared plus 1, where f of x runs through all polynomials in R bracket x. All right, so just if you don't think at all, that's the definition of the quotient. But then you say, oh, but we have a division algorithm. And so we know that every f of x is equal to g of x times x cubed plus x squared plus 1 plus r of x, where the degree of r of x is strictly less than 3. Which means, and so, because the difference f of x minus r of x lives inside the ideal generated by x cubed plus x squared plus 1, that means that they represent the same coset. In other words, r of x plus the ideal is equal to f of x plus the ideal. So we can say, oh, every single coset corresponds to a coset whose degree is strictly less than 3. And so that means that we could say, oh, really then the quotient is equal to this. Oh. So this allows us to narrow down, right? We started off where our coset representatives were all possible polynomials, and we narrowed it down to those with degree 2 or less. And that is one way, so that is a way to construct rings of a given order. Sorry, I said rings, I meant fields. That allows us to construct fields of a given order, right? By doing a quotient of a finite field, or where the coefficients are in a finite field, right? So something like ZP bracket X mod some polynomial, right? If you choose an irreducible polynomial in here, you get a field and it will have a prescribed finite number of elements. What will it be? It will, so its order will be what? P raised to the degree, whatever this polynomial is, -1, so n minus 1. Where that polynomial has degree n. Okay, I'm gonna take a break here and then I'm gonna come back for office hours in a few minutes. So you can stick around or you can come back or you can not come back, whichever you prefer. But I'm gonna let my head rest for a few minutes. So if I don't see you in 10 minutes, then, or 8 minutes or whatever it is, then I'll see you on, oops, another chat. How do you conclude that R bracket X is, oh, how, you conclude that because their difference, the difference there is a multiple of that polynomial, which means that it lives in here, right? Which means that they are the same coset, right? So it's because f of x minus r of x is an element of the ideal, right? That's what it means for two, or that's how you check to see whether two cosets are the same. Oh, you know what? I need to stop this meeting so that I can shut off the Zoom recording. So that means I'm going to kick